Hi, so my presentation is going to be fairly short. It shouldn't be more than 20 minutes, so thanks for hanging out with me for a little bit. My presentation is going to be very similar to what you just heard with Prem, except I'm going to take it a level higher. What I want to share with you today is what we see happening in what we call the mobile influence market. I also refer to it as the adjacent markets. So I go back a ways. I cut my teeth on developing products back when the PC industry just started. And the PC industry created a demand for adjacent markets such as test equipment, POS terminals, and industrial controls. For me, I was actually a product developer. I was designing laser printers. My responsibility was to design the printer and also the test capability in manufacturing. And so I and people like me, once the product was designed, we leveraged the PCs because of their standardized APIs and hardware, and they were ideal. The PC started out, its main function was originally spreadsheets, and then it expanded to other desktop applications like word processing and that sort of thing. But it quickly went way beyond that. In the same way, the mobile industry is experiencing the demand in high quality, low-cost components in mobile influence markets. So if you look at the graph on the right, I took this off of out of our sales database that shows our pipeline of different applications. And you'll notice that the consumer market, part of that is mobile. But the consumer market by itself is 20% of the activity that we see, or 25%. And the mobile is a smaller portion of that. So there's a lot going on outside of mobile. And if you look at the bigger slice of that pie, it's in industrial. And then following that is drones. Now I'm showing, let me go ahead, drones, automobile, AR, and VR. Now this is this is a percentage of what we see in design sockets, not in volume. So I'll talk about displays. Traditional displays on a handset, you'll have a front mount display. Sometimes you'll have something in the back. And so there's no big load on the AP. The AP can either have, if it does have a second display, it'll either use a second DSI driver, or it'll use a simple splitter to split between the front and the back display. But what we see is a lot more than that. We were seeing appliances using either DSI screens or maybe APs with DSI drivers. Automotive, where they want to take advantage of either APs or the AP or the displays. And then industrial. Industrial is, their main interest is larger displays. So they may want to take advantage of the connectivity of an AP and interface it with the larger LVDS displays. Where it gets interesting is with AR and VR. So typically, the AP may only have one DSI pipeline, and you want to drive dual displays, one for the right eye, one for the left eye. There's a number of ways to do that, but in general, you'll put both images in one pipe. Typically, they're concatenated left and right, and you'll need a splitter that can take line by line or frame by frame and send them to either the right or left eye. Additionally, there may be yet a third pipe that goes over to an HDMI bridge, so you can have a monitor sitting on the outside. Now, first I want to discuss, though, I don't know if Prem went over that, but there's a couple of ways to merge these pipes. Our terminology is mux versus merge. I don't know if that's a standard term. But in the mux application, you're taking one frame, sending the whole frame over, then you're switching over. It's essentially like a brute force switch. You're sending over the other frame, then you switch back to one frame. So you're seeing frame by frame. So the input pipe is the same bandwidth, where the output pipe is pretty much the same bandwidth of one of the input pipes. On the other hand, the merging application actually takes the two images and butts them up right against each other. So you send over line 1 of camera 1, line 1 of camera 2, so essentially you have the twice the aspect ratio of the input signals. Now, what you get on the output is twice the bandwidth. The advantage of MUX is it's a less expensive approach. It's easy to do. The disadvantage is latency from frame to frame. And what we see especially in, and I'll talk about that in another couple frames, the latency is a big problem. So I'll go to cameras. Cameras presently in the mobile market, their applications are fairly simple. It's you can have a front camera or a rear camera. They don't talk with each other much. You either have one turned on or the other. It's fairly straightforward. With AR and VR now, you've got environmental awareness from the camera perspective that you've got to be concerned with. Now, very simply, you can use an IMU, an inertial management unit. And this is, the responsibility of the IMU is to take a 3D accelerometer along with a 3D magnetometer along with a 3D gyrometer. You fuse the three together, and from that you can get a good perspective on where your head is at any given time. The problem with that is that over time, your head location tends to drift. So it's not a big deal with virtual reality because everything is a relative movement. But when you get into augmented reality, things are absolute. So in the augmented reality case, I may have my pet monster sitting on the table over here, and as I'm moving around talking to you, drifts tend to come to play, and that my pet monster might start floating off in space. So what you need in that case, and what we see people doing, is using cameras to actually identify places out in the field that are absolute. And the Google Tango uses that technology to keep that monster sitting on the table no matter where I happen to go. So cameras will do distance measurement and also a more reliable form of environmental understanding. So I'll talk a little bit about AR and VR tracking. So originally, the easiest way to do the tracking of your position of your head and your body is to put separate sensors and transmitters out in your room. Now, there's a couple disadvantages of that. One disadvantage is accuracy. The other disadvantage, I've lost my monitor. The other disadvantage is you've got to mount those transmitters everywhere you go. So if you want to use it in your home, you got to mount those transmitters up. If you want to use it in another room, you got to move them. The other, and that's called outside-in technology. So they've moved to inside-out technology. With inside-out, and I'm showing you here an example using the Microsoft HoloLens. The reason I chose that is because it's really obvious where their sensors are and what they're doing there. But in Microsoft HoloLens, they've got a pair of stereo cameras on the right, pair of stereo cameras on the left, and then they have another camera in the center, which is a time of flight sensor, which is used for distance. So the problem that you have there is now, going back to the original mobile concept, where you got one camera in the back, one camera in the front, they're being used at different times. Now you got 4 cameras, and plus another dissimilar camera that's attached that has a different resolution. So where did this start? It started, this is our experience. We started talking to AR and VR vendors, and they liked us because of flexibility. Their initial need was they got 2 cameras on a head-mount display. They want to merge them together. They want to do the merge concept instead of the mux concept because they couldn't deal with the latency between images. Then within months, no, they needed 2 cameras plus a time-of-flight sensor. And right now, they're working on 4 cameras plus a time-of-flight sensor. We're actually talking to customers now that say they need a lot more than 4 cameras. So things are changing. And it's all leveraging the MIPI technologies. So what else is there? There's 360-degree cameras. Very similar to the head-mount displays, except in some cases, there's even more cameras. Drones. Drones are worse. So you all know drones. The primary camera on a drone is what's used to take a picture of your of real estate, or law enforcement is using it. But there's a lot of cameras that are used for navigation. A lot of cameras. And so we talk to drone vendors. They're talking 6, 7, 8, 9, 10 cameras that they want, and they don't want latency between them either. Automotive is the same deal. Except with automotive, you also have the issue of transport. Then there's everything else. So there's the LVDS to DSI, where you have an SoC that can only do LVDS out, but yet you want to take advantage of the DSI display. The vice versa, AP to an LVDS screen. Dual LVDS screens. You have CMOS RGB to DSI, CMOS RGB to CSI, and then so on. And also there's the issue of retiming. So if you have a more complex system, you're sending a CSI signal, say through a couple of connectors from one PC board to the other. We've seen issues where you want to or need to retime the signal. So, why FPGAs? Why are customers coming to us? The first one is flexibility. FPGAs in general have general purpose IOs, but in addition, there are a class of FPGAs that are coming out, which we're part of, that include MIPI DeFi, or a lot of MIPI DeFis. FPGAs also provide an array of flexible programmable logic cells that can be used to support the high-speed data flow. It's used to support the protocol for DSI and CSI. The DeFi is typically hardened, in addition to splitting and merging functions. Why FPGAs? Another key one is time to market. So on the graph here, I show that the typical design cycle for a consumer product is on the order of 6 to 12 months. 6 months. 6 months from concept to delivery to manufacturing. It's a really short design cycle. And you look at the design cycle of ASICs, they're on the order of minimum 18 months. Okay, so the ASICs can't keep up. They're a generation behind, typically. And we see this in MIPI DeFi, we see this in SPI to I2C protocols. It's especially in the consumer market, it's evolving so quickly, the ASICs are having a hard time keeping up. So they come to us. The other thing is that the design cycle between us and ASICs is very similar. Okay? The only difference is risk. So the reason why we can go quicker is the ASIC design cycle is very risk averse. You make a mistake on that, it's expensive. FPGAs, you make a mistake, it means another iteration of a couple days. It's a problem if it gets into the product and out into the field, but that doesn't happen. Usually there's a lot of upfront testing that goes on with that. So what we enable, what FPGAs enable is fast time to market. And I will say from experience, a lot of the consumer customers that we work with, sometimes we'll help them with design, sometimes we'll do a complete design. Very often they'll do their own designs. But when we help them, the spec that we write is typically on the order of 2 to 5 pages. Right? Look at the spec of an ASIC. It's not 2 to 5 pages. And the reason is the customer has his best understanding. He wants to move quickly. 2 to 5 pages, he wants to start the design now. And he understands that we are willing to make the change in flight while the project's going on. Very often, their needs may change. The market may change. And we make changes while we're going. So that's it. MIPI components are becoming ubiquitous. I'm seeing this, it's a deja vu all over again. This is what I saw in the PC market 25 years ago. And everyone is leveraging PC components. Cameras, displays, APs, accelerometers, you name it. Mobile influence markets are leveraging these components in all sorts of combinations today, and I can guarantee you if I'm up here next year, I'm going to have a completely different set of applications that are being used. And FPGAs have been instrumental in enabling these new and unforeseen markets in ways that simple bridges can't. Thank you very much. Any questions?
Hi, Tom. Thanks for your presentation. The point you had in the slide where you had bridging to different interfaces was very interesting, especially LVDS and DSI and things like that. Bridges to multiple different standards, and I could include EDP or HDMI is getting to be more and more an issue because a lot of people have one interface and they need a bridge to it. Would having MIPI standardized bridges, especially in mobile influenced applications like automotive or IoT, be something that Lattice and other FPGA vendors could really get behind? And because it seems like it could help you out a lot. So the question is multiple, bridging, making a standard for bridges, and going from one common interface to multiple varied interfaces. Is that something of interest?
I don't know how you do that. I'll tell you why. We have we have two different approaches that with our. So I'm referring in this talk to our crosslink device, which has hardened MIPI D-PHYs and it has some soft MIPI D-PHYs on the other side, and we originally approached this product as a PASSP, programmable ASSP. In that case, and what we provided the customer is a set of standard bridges from input to output. And what we found is the customers really like that idea. We brought it into them, and within a half hour, the discussion migrated from, gee, that's a great solution, but gee, we have a unique opportunity to get into a specific market. Can you change these tiny little specs? So I don't think we had 10 of these complete end-to-end solutions, and I don't think any of them went out to the market untouched. So I think it's going to be really hard. Part of the maybe if these were ASICs and the customer knew he had no choice, maybe he would force it to work. But I think in a lot of cases when the customer knows he's using an FPGA, he knows he can take advantage of that. So I think it's going to be, I think it'd be really tough.
Thank you very much.
So having that flexibility with FPGA is definitely a great plus, but I'm curious to know what kind of trade-offs or cost does it come with in terms of power, area, cost, or anything else?
Okay, so so the question was, what are the, if I heard it correctly, what are the trade-offs that you have to make with an FPGA in terms of cost and power, in particular, right? So I can talk about cost. So our FPGAs in general are, getting back to the flexibility issue, we provide the IP for the input, the IP for the output, and the customer designs specifically for what he needs. So in terms of cost, in general, we're able to fit the specific application into a smaller IC. So most ASICs have a broader range of capabilities, and so they take up as much or more silicon. So from the competitive standpoint, we compete head-to-head with standardized bridges. From cost, power was your next question? Okay, from the power perspective, it's sort of the same situation. An ASIC is a device that is designed to handle a broad range of bridging solutions. And so from the power perspective, you're rattling the whole FPGA, you're rattling the whole ASIC, all those signals to perform your narrow set of functions, even though that ASIC performs a broader range. So with our design, you design it specifically for what you need. The rest of the FPGA that is unused doesn't wiggle. So we find that we have actually better power. There's another specific feature that we have, is that we have the ability to go into sleep mode. So if you want to take your system down for more than a couple frames, you can put us into sleep mode, and then we're down to microwatts at that point. So we find that we compete as good or better than ASICs in that perspective as well. And then once you talk about cost, that really relates to the size of the silicon. We tend to be about the same size or smaller. Thank you very much.